Welcome to the lecture on data manipulation, part of the Principles of Data Visualization lecture series. We'll begin today by discussing what we'll be talking about in this lecture. So first, we'll discuss a number of data visualization framing principles, important basics of data visualization. Then we'll talk about some approaches to data manipulation, and then we'll conclude with the visualization design process. Now let's start out with the discussion on good data visualization, a good data visualization frame. What does that look like? Well, first, it has a great title. So let's take a look at this title. In climbing the income ladder, location matters. So who does this apply to? So as you might have surmised, it's everyone, right? Everyone cares about income. Now it has focus some, it's restricted. Probably it's most interesting to an audience that's in North America or the United States, but it doesn't have to be. There may be a number of audience members from outside the United States that also have an interest in how this distribution looks across the United States. Now, a couple things about titles. They should be direct, brief, and frame everything that's going on in the data visualization. Now, if we have to give on one of those tenets, we would give and allow the title to be longer in order to capture everything that's going in and properly frame the data visualization. But wherever we can, we want it to be succinct and to the point. Also, our titles should, all the words in the title should be capitalized. And from time to time, there might be a few, like by or per, that some organizations might have preferences for keeping those lower, but many of them just provide a standard of all words in the title are capitalized. Now, moving down from there is the subtitle. So our subtitle here is "A study finds the odds of rising to another income level are notably low in certain cities like Atlanta and Charlotte, and much higher in New York and Boston." So what we typically do in the subtitle is we position the insights. So whatever it is that's interesting or unique or unexpected in the data visualization, we want to position that with the subtitle. And you see that the New York Times has done that here. They've referenced income levels. They've highlighted that Atlanta and Charlotte are low. They suggest New York and Boston are higher. And then if we look down, there are annotations for each of those. So they have a plotted point on Charlotte, and out to the right, they've defined with the label of Charlotte 4.3%. And what they're defining here, this overall map, if we look over on the left-hand side, is a probability map by county. So if we look, the chance that a child raised in the bottom fifth rose to the top fifth. So what this map is a measurement of what is the probability if a child was born in the bottom fifth or bottom 20% of the population, or bottom 20% of the income level of a population in a county, what is with that a given, what is the probability that they will raise to the top fifth? So basically go from the bottom 20% all the way to the top 20%. So that's the metric or algorithm that's at work here. So our scale here, that starts out at 4%, 10%, 15%, 20, 35, basically works like this. So a child born in the bottom 20% of a particular county, what's the probability a child goes to the top? So it could be 4%. We'd tag it in red. So 4% of those 20% go to the top fifth. If it's yellow, it's 10 to 15%, green 20%, blue 35%. So basically a third of that bottom 20%, if it's blue, rises to the top 20%. So basically, this is a map of rags to riches probability. That's the idea here. So underneath there, the New York Times diligently goes a little further and says the top fifth is equal to family income of more than $70,000 for the child by age 30, or more than $100,000 by age 45. So they're basically adding, and here's why it's important. I think most of us probably would already know why income is important, but the New York Times makes sure here. Now, coming back to the map, apologies. Take a look at the map, and let's see where we think the best location. So imagine that you were born in the bottom 20% of a county in the United States. Which county would you like to be born in? And so you can look all around the map and basically choose your county. Take a couple minutes and kind of take all this in and then see what your choice might be. Now, if you're like me, which most of you guys are, many of you would probably take a look at the blue regions, because you'd say, hey, this is a probability game. If I'm born in the bottom fifth, I definitely want to get to the top fifth, and I want to increase my chances of that as much as I can. So I am going to encourage my parents, or as a parent, I'm going to move to this particular county. And we might take a look at, for example, the counties around Salt Lake City. We've got some green and blue there. We might also look at both North and South Dakota, quite a few blue areas there. We might look out in West Texas, predominantly in the counties where the oil fields are. We might look in western Oklahoma, or in some of these central states, western Kansas, Nebraska, etc. And the reason why is because we see that our probability is much better in these locations. So we might choose those. Now, coming back to what the New York Times has said. So the first thing that they said is it's notably low in cities like Atlanta and Charlotte. So we look at their two annotations and we find, yes, it's absolutely true that in Charlotte and Atlanta, those areas are highlighted in red, which means there's only a 4% chance that if you're born in the bottom 20%, they're going to make it to the top 20%. And they include a little annotation there that says in areas like Atlanta, upward mobility appears to be substantially lower than in any other rich country. So that all makes sense. That fits our scale order. Now, the next thing they say in the subtitle, and much higher in New York and Boston. Okay, so we look up at New York and Boston. We say, yes, that is true. New York has 9.7%, Boston 9.8%. They're both in that roughly 10% category. So the odds are definitely better in New York and Boston versus Charlotte and Atlanta. But there's one thing that seems to be a little funny about this. And this is, at this point, I want to introduce to everyone the concept of bias. Every data visualization has bias. Even the most well-intentioned, principled, objective analyst, as soon as they begin to frame a data visualization, their background, their experiences, their particular preferences, sometimes consciously, sometimes subconsciously, begin to take hold of the work that they're doing. And so now I'll bring your attention to, if we were creating insights, typically we're going to focus on which ones are the lowest probability and which ones are the highest probability. Well, the ones that are the lowest probability, they have accurately there is Atlanta and Charlotte. Now, I'll suggest to you, this is the New York Times. So a potential bias that's here is that if you live in New York or perhaps in Boston, you may have a built-in bias against folks in the South. There's stereotypes that are there. Folks in the South are slow. It's sort of backward in the South, that sort of thing. So some of these biases are there. So it's quite possible that if you're from New York, you will very quickly seize upon some of the information, like the cities of Atlanta and Charlotte. Now, the more peculiar selection is of New York and Boston for the insight example of an alternative insight. My question is, it's sort of mid-range here. It's sort of mid-range to low, and they're defining New York and Boston. Now, why might that be? Well, perhaps we're from New York. You know, New York is the center of the universe, and of course, everything great is in New York. But maybe not so much. And so perhaps a more objective subtitle might have ended something like, and much higher in Salt Lake City, or much higher in the Dakotas. Something like that. That might have been a more objective and accurate representation. With all that said, I present this to you guys because this is an excellent example of a very professional grade, publishing grade, could go onto a news media website tomorrow, because this, in fact, came off of the New York Times website. So I present it to you as an example of absolutely what to do, with an acknowledgement that we all need to keep in mind what our potential biases are. And the best way to handle those is to put notes and annotations right up front that says, the way that we've constructed this data visualization may bias these certain things in this way. And if we've put that out front, we'll be viewed as a very objective, highly professional data visualization analyst. Now let's move on to one that's maybe just a little bit simpler. So here we have a number of trend lines. This is a great example of single axis plotting. We have time across our x-axis, so we have different data plotted by months across a span of about 10 years. Then on the y-axis, we have measurements of months of supply. So our variable there is how many months of supply do we have? And this might be something like in the real estate market, how many months of supply do we have? And we can notice here that as we get into 2008 and 2009 during the financial crisis, the months of supply of homes available spiked up quite a bit. So this just gives you a good example, very simple, straightforward, single axis trend line plotted across a timeline or across a time series. Notice that we have a label on the y-axis. You could argue that it's self-explanatory that the x-axis is self-explanatory, but our preference would probably be to include a label there like calendar year if we were doing this for a business presentation. So here's an example of multiple axis plotting. Somewhat similar to the previous, but in this one we have 8 unique measurements that we've represented in terms of a bar chart. So we took these 8 different measurements, measurement 1, measurement 2, etc. through measurement 8. On the left-hand side, we have the Celsius temperature scale, and on the right-hand side, we have the Fahrenheit temperature scale. And these happen to be synchronized because the temperature measurement is exactly the same. We just have 2 different scales, the Y and the Y2 on the left and the right of the visualization. But we can also create multiple axis visualizations with different scales. For example, sales on the Y and profit on the Y2. We might overlay those two. So just to give you an example of some other basic data visualization principles. Now on to data manipulation. So why do we need to manipulate data? Why is that the case? So as many of us know, and most of us are coming to the conclusion, data in the real world is rarely formatted the way we want it to be. We often have to reformat data. Certain software applications format data in certain ways, particular file types, and then other software applications that we want to use that data in require different file types. So often we have to reformat that data and make adjustments based on how we want to use the data. As well, when we reformat data, it can help us repurpose particular data sets. So a data set may have been intended to be used by one particular piece of software or for one particular purpose, but we found a new way to utilize that data set for a different type of analysis, or we enhance an existing analysis that we have with more context by repurposing a data set. Now there are several different methods of formatting. Probably the most common is through data formatting applications. So there are particular software applications that we can put one type of data format file. We can basically upload it into the application and then save it as an alternative data format. So that's one of the methods. The second method is manual formatting, and probably all of us have done that at one time or another, formatted some data in Excel. And the third method is applying programming methods, where we can format or reformat data with a program. And so we're going to go through each of these. So the first one. So we'll take a look at data formats in Excel. So we might receive an Excel formatted data, so something like XLS. We might have delimited text, so basically a CSV file, which stands for comma separated values. And basically what that is, in between each value, we have a comma, and then we have the next value. And in this particular data set that we're looking at on screen, we're looking at the date, basically the date and time stamp, then the name of a particular storm. These happen to be the name of severe weather storms like hurricanes, the measurement of latitude, longitude, and then the average wind speed. Hopefully that gives you a feel, and you can see the commas between each of them separating. We can also have tabs, semicolons, pipes. There's several different delimiters that we could use that are notated as comma separated values. So a third type are JSON files, so JavaScript object notation. Basically, data is presented in name value pairs. So first name is the name of the field, and then John is the value pair, or the value, if you will. So basically we're pairing together the name of first name and the value of John. Now with curly braces in JSON formatting, we can hold objects and data separated by commas. So here we have a small series here, basically just two name value pairs, first name being John, then we have a comma, and then last name, we separate those two with colon, and then Doe. So basically first name and last name is John Doe. Our square brackets will hold an array. So we go up one more level here and say, oh, what if I needed all employees? So you'll see we put employees here as a name, and then we'll have a number of value pairs in the square brackets. You'll also see the curly brackets within there, and they're different combinations of names. So we have John Doe, Anna Smith, Peter Jones, etc. Now, another look at that example and basically HTML code. Here we have our employees, and then you'll see the square bracket begins after the equal sign. Then you see the curly bracket on the next line, first name, last name, closing curly bracket, comma. And this is the notation, often the notation that we'll use in JSON, where we put those, we start off those curly brackets on one line, we put the values in between, and then we put the closing curly brackets on the next line, and then a comma. So that's kind of the way we format them in HTML code. We also have extensible markup language. So with XML, it works similar to JSON or EDI, if anyone's familiar with that, where we have different tags The tags basically describe what's in the field. So all XML elements must have a closing tag. So we see here we have the beginning paragraph, we have the contents of that, which we've simply defined as this is a paragraph, and then the closing tag of a paragraph or closing paragraph. XML elements must be properly nested. So we have these two tags here, bold and italic, to adjust this text. Case sensitive. So the content that we put in, capital message is different than lowercase message. And all those XML elements must be properly nested again. And here's an example of extensible markup language, XML, being utilized within a code example. So we see the menu there, a number of menu items, header, different item actions, and then we close out with the closing menu tag. We can also have files from the Hadoop file system. So one of the versions of big data files. So the Hadoop sequence file format consists of a binary, key, and value. So basically, we're pairing that binary key on or off, and then a value. We have three different sequence file formats. So the first one's uncompressed, the second one's record compressed, and then the third is block compressed. The sequence file consists of a header followed by records. So let's take a quick look at those. So the file header, we have basically the sequence file that defines what we have. So we basically have the sequence and then the version. We'll follow that with the key class name. Basically, what's the key for this file, and then the value. Boolean is compressed. It's block compressed. We'll have metadata and a sync marker, and then we connect that header to the records. So if it's uncompressed format, we start off with the record length. So basically an integer that represents the key length plus the value length. Then next comes the key length, and then the key, and then the value. And so basically in the record you have fairly similar to object notation. You have a set of pairs, basically a key and then the value for that key that connects to that key. Record compressed format, so you'll see that file header is on the left. Then you'll have the first record, and then a sync, then the next record, and then a sync, etc. Through n records. So basically, with record compressed format, you only have the values. And then the block compressed format, you have everything except the record count. So here we have the header, the block, the sync, then the next block, sync, etc. through the sync to the block N, or whatever number you have there. If there's 100 entries, it's block 100. Okay, so several different formats of file that we could have, we could receive, that we might need to use or convert. Now, software formatting tools. So we could utilize Excel spreadsheets. So probably all of us are familiar with Excel. Google Refine, a utility called Mr. Data Converter, and then we'll talk about the Python programming language. So first, let's talk about Google Refine. So Google Refine is pretty powerful. It's an easy-to-use tool that helps to format messy data. As with a lot of tool sets from Google, it's available online at no charge, and you can cleanse data using transformations, clustering, filters, some of these functions. So it has quite a few extensive functionalities, as well as it's pretty easy to use. So it has a little bit of the look and feel of Excel. So as an example, what we see here in front of us is a Google Refine view of data. And you can see we have basically grid layout here. So we've got a bunch of rows, a bunch of columns. We can see in some cases some of our values are missing or are null. And in this case, we want to change our view to include what's called a facet view, or a text facet. So here we'll go to the column of type, and here we can see things like different types of disasters, earthquakes and storms and that sort of thing. So here we're going to click on the menu, a facet and text facet. And when we do, we'll receive this view to the left. This window to the left opens up. We'll notice that our total records in the type field is 17,828. And the number of distinct values is 18. And so what that's saying is there are only 18 unique value entries in this column. So you can have complex disasters, drought, earthquake, epidemic, etc. There's 18 choices, but it's only those 18 that are available. And out to the side of it, so if we take a look at earthquake, in parentheses, seismic activity, you'll see that there's 1,120 entries in that column for earthquake. So it gives us a sense, this just turning on this facet view allows us to also get a sense of which values are the most popular, what's the cross-section of values, sort of what is our distribution of those values in the column, which is much, much easier than if we tried to eyeball this. So if we tried to eyeball 17,000 different entries, we'd start reading through. We might make it to the first 100 or 150, and we're like, this is too many to process. So this helps us, this facet view helps us refine it down to these are the unique values there. Now we also see, if you'll read further down, we see that there may be some consistent or repeating values. So we see mass movement dry, and then a second mass movement dry, and the only difference between them seems to be the capitalization on a couple of words. So we might deem that these are actually the same thing. And if they are, we can click on the cluster button. And we will see the redundancies and duplicates in the type field window here. And for each of these, so the first one we see there is the mass movement dry, and it looks like there's a different capitalization on each. So we can choose a couple of different things. We could just exclude these, or we could click on edit and go in and basically edit the values there of that phrase to match the other phrase, so that they would then join as basically just one phrase, mass movement dry, each word capitalized, and it'd have a quantity of 52 out beside it. In the same way, we could select edit and correct the capitalization on transport accident and join those together as well. And here we've done that. So after correction, so after we've corrected those two, we'll see that the types have gone down to 15 versus 18. So we have those 15 categories, and we'll see that the quantity has increased on mass movement dry and transport accident. Okay, now Mr. Data Converter. So Mr. Data Converter is kind of a simple, straightforward utility that was built by a data analyst named Sean Carter, who works at the New York Times. And the application was built to do file conversions because the analysts found themselves needing to convert from one file format to another with the different tool sets, with many different tool sets they were using. So this application was created for that purpose. So it's a simple and free tool. You can convert Excel and CSV data into XML or JSON or other formats. And it's very useful, particularly if you're doing data visualization on the web. So here's what it looks like. We can paste CSV data in the input area. And then in the output header there, we can select what file type we want it converted into. And after we select that, it will go ahead and convert that data from the input file into an output file that's in the format that we requested. So that's fairly handy. It's very quick and efficient as long as the types of file formats that you're wanting to convert from and to are supported here. Now we can also do lots of formatting in spreadsheet software. So spreadsheets are excellent software to make changes to individual data points. So that's the place where Excel earns its keep. So there we have very easy sorting and filtering in Excel. We can do very quick formatting. We can do conditional formatting. So if this particular condition, format in this way. And probably the most popular or commonly used is text to number manipulation. Often we will have data sets that we want to utilize. A particular set of integers or numbers is captured as text, but we need to convert those back to numeric integers before we utilize them. So here we have an example of spreadsheet software. We're formatting a table. So if we drop down, we can see lots of different color schemes for formatting this particular table in a more pleasing way. We can also have what's known as conditional formatting. So when we click on a cell, we can click on conditional formatting. and go to the menu that would set that particular formatting or that particular set of rules for us, where we might define that formatting rule, if then type rule. So here you can see we have a couple different selections. The first one on the left is turning text into a number. The one on the right, we're turning a number or integer into currency. And so hopefully you get a feel for, okay, this is some of the things that we might need to reformat. And, you know, particularly we might be able to bring this into focus if you try and add, subtract, multiply, or divide two text fields, even if they look like numbers, you're not going to get a really good result with that. They have to be formatted as a particular integer to work well. And we can also do formatting using a programming language. Now this is often very useful in situations when our software cannot handle very large data files. And we do run into that from time to time. So programming provides us with a great deal of flexibility for tailoring scripts specifically for our data set. So as an example, this is an example of a data set that we are asking you to reformat. I've worked through this data set before as well. You'll notice that the two columns in this data table are place and state. Now, let me explain a little bit about that. And most of you guys, if you looked at it, say, oh, it's labeled wrong as place, it should be city. Now, there are a number of different towns, cities scattered throughout the United States, and they can be unique and distinct. As an example, I might ask you guys, where is Dallas in the United States? And many of you guys might immediately rip off, it's in Texas. But we might have left behind Dallas, Georgia, which is also an appropriate Dallas for the United States. We might also find large collections of cities and townships named Lafayette. Now, we have at least two, one in Louisiana and one in Indiana, and there's a very good reason for it. So Lafayette was the French admiral, some might say general, that helped the colonists in the United States win the Revolutionary War. And so we thought quite a bit of Lafayette and rewarded Lafayette by naming quite a few towns across the United States after him. Now, we've also got other issues that can occur. So the 5 boroughs in New York City were actually 5 different townships before they were New York City or before they were boroughs. So if we go back in history, and all this data is census data in the United States, and you can see that the first year is taken in 1790, and then every 10 years after that. Now, particularly as these cities and towns grew, sometimes you might have a city or township in one census, and you get to the next one, and it's no longer there. For example, the 5 boroughs were turned into New York City. We might also have situations like Philadelphia, where there were several townships that were sort of like neighborhoods in and around Philadelphia. At a particular point in time, Philadelphia basically annexed these different towns, and it became Philadelphia, the large city that we know. Now, coming back closer to your assignment, you'll notice a couple of things, that place and state are separate. And I've mentioned to you that in order to make these entries unique, a good way that we can approach that is to take the place, whatever the place is, with a dash, and then the state. And that gives us a unique identifier for that particular place and state. We might also need to transpose the years in population in our data set. So here we might have the census in 1790. We have a population in New York City, but none to speak of in Los Angeles, Chicago, or Houston. And so you see those blank or not reported. Now, in order to utilize certain types of software, particularly Python, we might need to create a particular data layout set that's different than what we're looking at here, to avoid all the problems with these null values in the cells. So one of the things we might do is transpose that years in population. So we might have our location, then we have the column of year, and then we might have the population in a third column. Now, once I have that data file, I can load that into a Python program, and I can even choose to reformat the data in Python if I would like to. And this is what that programming language example result might look like. So if you recall, one of the main tasks that we had to do is to create unique locations. And I've explained how you could have the same city twice in a state, or the same city in a couple different states. And to make sure that we're unique, that this is a unique identifier, we can turn it into a location or state dash place where we have the state, for example, New York dash space New York City. And as well, New York City might have just been a town in 1790 that didn't include all the boroughs. And so you'll see in the second column, the year is 1790. And if you look down, we have several entries for 1790 in the different townships. And then the population in 1790 for each of these locations is defined in the third column. So we're basically reformatting the image on the left into the image on the right so that we can do some further analysis on it. Now we'll discuss a particular approach, process for managing data manipulation in the context of data visualization. So this particular process model was put together by Tamara Munzner, an outstanding data visualization academic that's done a whole bunch of work, and I think 1 year ago was awarded with sort of data visualization person of the year by the major academic conference. So that's where it comes from, and basically it's called the 4 nested levels visualization. So the first part of it discusses the domain situation, then the data and task abstraction, how do we do visual encoding, and then do we use an algorithm? And we're going to walk through each one of these and explain what each piece or each level of this is. So first we start with the data domain. So I'd like to explain data domain perhaps with some stories, some analogies. So how do we know what a data domain is? So understanding of data domain is a familiarity with different relationships of data elements in this type of data. So it's often classified in terms of industry. So unique industries use particular types of data. And to provide a real-world example here, we might have a whole set of sensors that are installed on pipelines or in energy or oil drilling type industry or application. The folks who have installed and perform quality assurance on those particular measurement devices that create measurements and track data, they may understand particular nuances between one manufacturer of a sensor and another manufacturer of a sensor. Manufacturer A, their sensors may always read just a little bit high. Manufacturer of sensor B, their sensors may always read a little bit low. And it's only through having that experience that you'll completely understand how those measurements are taken, what the nuances are, what some of the differences could be, what could account for differences, and a basic understanding of what each of the data fields are. And I want you to think about maybe a simple Excel spreadsheet, a set of data that we've captured for maybe an Internet of Things device. Each of those columns has a column heading. Now, we may look at the column heading and we may understand the words that are in the column heading, but we don't truly understand the full definition of what that column heading is. And so often what you'll see when data sets are published, you'll see the data set published with the column headings, and then you'll see an index of definitions for each of the fields that are in that particular data set. So you'll basically see the column heading and this column heading means, and then a 1, 2, 3 sentence definition of what that particular variable means or column means or set of values means. So the data domain is basically data neighborhood, and understanding the data domain is basically a product of having worked with the data for a great deal of time, or leveraging individuals who have. Now, sometimes the data domain is used for a classification of different fields. So we have different fields in academia, different fields of thought, different fields in industry classifications. And a good example of that in the visualization, in data visualizations, we have 3 unique fields within it. So InfoVis focuses on information visualization. How do we take information and encode it with visual elements? It often is focused on things in business or journalism that have a lot more to do with human communication. There's also SciViz, so that's a different field that basically focuses on different ways that you can visualize scientific or biological processes, techniques, objects, and so you might find some interesting ways to visualize shapes or animals or medical processes and techniques. And there's also VAST, and VAST is a third field that's primarily focused on visualization analytics. Basically, how can we use data visualization as an analytic technique? And each of these three fields are unique and have their own terms and their own approaches. Now, there are often different philosophies on, what is a data scientist, and there are some who believe, hey, if I have a good data scientist, or if I call this particular person a data scientist, they can take any data set and provide great insights from that data set. I happen to believe some of those things are true, but not all of them. And part of that is from experience in the IT industry, where we've been through several of the same type approaches, where you may be a particular expert in a technology or a particular approach or an implementation approach, but you may have a more limited understanding of a business process or an industry or the inner workings of a business process. And so I'm a fairly strong believer in leveraging subject matter experts. So let's say we have a data set. Perhaps it's on different DNA markers. Now, I'm not an expert in human DNA. Might have a different data set that's on different pharmaceutical compounds. I'm also not an expert on pharmaceutical compounds. So if I'm analyzing one of those data sets, I might want to go find a subject matter expert from that data neighborhood that understands how those measurements were captured in those data sets to help explain the definitions of each one of those variables, as well as what some of the nuances could be in the variance of the values. I think we should always be asking good questions. So remember that that's a fundamental principle of Bertin, as well as John Tukey, sort of the fathers of both graphics and visualization theory, as well as statistical analysis or exploratory analysis with statistics. So that seems a good practice, to be always asking good questions about the data set and what it means. And then ultimately, what we're trying to do in the data domain is come up with a definition of our requirements. So it's in that data domain that we understand this is what the data set requires. This is what we need to know about the data set. And so hopefully this is help you get a sense of this is what it means to have a data domain. Now moving on to the next nested level is a discussion on task abstraction. And I've put in parentheses user experience because many of us have come from technology or IT fields, and we already have an understanding of what user experience is. And so task abstraction is just, it's a term that Tamara Munzner came up with. She created that term. But its meaning is very, very similar to user experience. And so I would describe task abstraction, basically, what do you want to do with the data, is a very similar, if not close cousin of user experience. So what we're trying to do with task abstraction is to define the functionality of the visualization. So what's the visualization going to look like? Will it be an overview? Will we be browsing through the visualization, looking at one area and then looking at another area? Will we be making side-by-side comparisons? This one's at this level, this other one's at another level. Will we be doing summarization? So will we combine or aggregate or roll up certain data elements? Inversely, will we drill down and parse and fragment particular components of a summarized data measurement? Will we do filtering? Will we strip out certain data values? Will we try and do synchronization between some visualization elements? And last, will we deploy some type of animation for looking at our data visualization? And you'll notice all of these things have a lot in common. They're all sort of features and functionality of how I look at data visualization. So from there, just a reminder, so we've discussed the data domain, the domain situation. We're in the middle of discussing data and task abstraction. So some examples of task abstraction when I'm doing analysis. So I might, in a consumption mode, I might discover particular aspects about a data set in a visualization. So here you see we sort of have a magnifying glass. It's moving across a distribution. We might be finding that it's a normal distribution, an abnormal distribution. It's skewed in one way or another. We might be comparing some of the measures there. So here we're discovering. I might also present. We might present some data visualization in a descriptive way to communicate. And then finally, we might simply just enjoy data visualization. And there are examples of some data visualization, particularly animated data visualization, that we could simply just enjoy watching as that visualization runs, perhaps over a time series. In producing, so we might annotate. So we found some unique insight or aspect, and we place a tag. And so if you remember at the beginning of this lecture, the New York Times was placing annotations or tags on particular cities in the country as part of the discussion on moving up the income ladder. We might record. So we might record several views of a data visualization so that it can be easily consumed at a later date. And then finally, we might also derive. So we might take one representation of data. For example, we might have a particular data column here. That data column represents a series of nodes and links in a network diagram, and we derive sort of what the center of that network is, or the most popular node on that network. So just some different examples of how we might do analysis, how task abstraction might work. Now we might do some searching. So we might have visualization where the target's known and the location's known. And basically we're doing a lookup. So we know, hey, we want to look up Richardson, Texas. That's our target, and so we just look that up on a map. We sort of enter Richardson, Texas, and it highlights that particular location on the visualization. We could also be in a browsing mode. So we don't really know what target we're after. So we're sort of, maybe there's a number of different cities or different data elements that we're looking at. We might know our general location, but we're not really sure where we want to stop. So we're just browsing around, looking for something that we find interesting in the visualization. Then coming back on search where the location is unknown, but the target is known. So we might have some stepper functionality, or we might just have some navigation functionality where we click on arrows up, down, left, and right, and that takes us through different parts of the visualization. My target is unknown, and my location is unknown. I'm just sort of exploring around, seeing what I see, in contrast to when my target's known, I'm trying to locate some particular data element, even if I don't know where it is. So in querying, when we query, we'll identify certain data elements. Then we can compare those. So we compare one trend line to another, and then we might summarize whatever that comparison is. So lots of different tasks, different ways that we could look at data, different techniques. And I would encourage everyone to read the sections of Tamara Munzner's book that I have defined in the syllabus that pertain to what we've just walked through on task abstraction. We also have data abstraction. So with data abstraction, we're talking about how the data is structured. And so the first one there, a data table, we might have different columns and rows, cells within it. We're probably all familiar with this type of data table or data structure that has columns and rows, basically a matrix. Then we move on to network data structures. So here we have different nodes. Nodes tend to be a noun or an object, an item, and then the links are the relationships between those nodes or objects. And we will discuss this in a later lecture on network visualization. Then we'll go to a grid of positions. So this one I think is maybe the most interesting of the bunch, and it helps to understand some of Tamara's background in data visualization, particularly in visualizing scientific types of objects. So imagine that this grid of positions, this arc, is your arm. And so your arm is basically an oval or an arc. So if this is the top of your arm, and then imagine you were trying to describe to a doctor where the pain was. And in some cases, as is marked on this grid of positions, the communication that you want to provide is it's on the surface, so it's right there, and we see that with the red cell that's colored in. We might also be trying to describe, well, it's actually near the top, so we might be sort of at the top of the arc, but it's underneath my skin. And it's even underneath that. So you're trying to describe something. Here, there's a way to actually describe it. We've got 4 different levels. A patient could communicate, hey, it's about halfway in between the bone and the surface of my arm. And that could be notated in the second or the third row there on the arc. And so a grid of positions doesn't have to be shaped exactly like this, but it helps us approximate where something is and capture data that pertains to that. So we might have geometry. So this is a spatial representation of data. So we're looking at particular position or a geoposition on a map. I think this one happens to be of Great Britain. Then we move on to our multidimensional table. And I think most folks will know what a Rubik's Cube is. Some folks may know it as a magic cube. And so if you can imagine sort of a 3D series of cubes, sort of like a Rubik's Cube, where we have different values in a cell for several different dimensions. And so here we're representing one dimension as key 1, a second dimension as key 2, maybe a third dimension as attributes. And we might have a value from each of those 3 dimensions represented in that cell that's highlighted, or in that cube that's a part of the overall cube. And then finally, we could also have trees, which is sort of like what you see in a network diagram, except it works in a more hierarchical fashion. So now we've discussed our domain situation, data and task abstraction, and we're going to move on to visual encoding. And what I've done for you is I've prepared our discussion on visual encoding using the features and functionality of how Tableau encodes data with visualization examples. One reason is to give us sort of a better picture of what is visual encoding. The second reason why I've utilize images from the Tableau software is it probably tracks as close to the academic literature, sort of the historic academic literature from Bertin through Jock McInlay, basically to the present day, that many of those principles are manifest in the Tableau software product. So we're going to use it to explain visual encoding. So with visual data encoding, we have several different visualization that we could perform. So automatic will basically dynamically adjust to whatever data selections we might make. So it's sort of a default, if you will. Then we can move to very specific sort of directive approaches to data visualization. A bar chart, for example, provides comparison. A line chart provides trend analysis. Area provides trend and comparison. Shape provides complex comparison. Maps give us a sense of proximity of different data elements in a spatial context or in space. Our pie provides us with a percentage contribution. Gantt charts provides a relationship of measures in time. And then finally, polygon basically creates different data areas, and from time to time we might use those different data areas. We might also create different types of maps or organization of our visualization of areas or categories. Now, we also have a best practices recommender. Okay, so one of the unique things about Tableau is it has a recommender system. So if I look at the data panel on the left, I've highlighted two different data elements, order, priority, and the market. And if I go over to the right-hand side of the screen and drop down on the Show Me tab there, this engages the recommender system, and we will see highlighted some proposals of data visualization types that you could use that might be a good fit for the data elements selected. And you'll also see some of the data visualization types that may not be the best choice fade to the background. Now, that doesn't mean that we can't utilize one of those that's faded to the background. So we can custom encode anything we'd like. But this basically just gives you sort of a vetting of what might be some good choices for data visualization types. Now let's talk about plotted points. So plotted points might be one of the simplest, easiest to understand visual encodings of data. So we have a point, basically we have an x-axis along the bottom, left to right, and then we have a y-axis, sort of bottom to top. And then we'll have different measures on the x and y axis. For each particular measurement, we will know what the amount on the x-axis was that corresponds with the amount on the y-axis, and we will plot that point on this view. We'll see, and we see here we have a whole bunch of plotting on the x-axis there, right at the zero amount of profit. So it looks like we've got a significant cluster of, customers that made a little bit of profit, some that didn't, that we lost a little money on. And in this particular case, we're looking at shipping cost along with profit. And that dynamic occurs basically up to about $800 in shipping cost. And then we start seeing representative examples in lots of different areas. Some of them, there's an outlier where the shipping cost was maybe $2,500, and we lost some money there. Over on the right-hand side, we have an example where The shipping cost was maybe $2,800, and the profit may have been near $4,000. So just an example of plotted points. So this is a simple way that we take data elements and encode them with particular types of data visualization. Now here we've done the same thing. We have plotted points on an X and Y axis, but we've encoded them with color. So we've drug a particular value. In this case, it's a category value. We've taken that data element, we drag it to the marks encoding there, and what mark stands for is just like it sounds. You're making marks on a page. These track very closely with Bertin's variables of data visualization that many of you guys may remember, sort of X, Y, Z, color encoding, texture, etc. Here we've drug our category field to color, and then we see our three unique data plots or data points there, each representing either furniture, office supplies, or technology. I can also encode with shape. So here I've drug market, so the field of market, to the shape mark, and what it does is it takes each of my plotted points and turns them into a unique shape to represent each market. And so now I can see I might have a data point that is technology, so it's green, and that is also representing the Africa market as a circle. And as well, I might have a triangle that is blue, and it is also representing the U.S. So it's furniture in the U.S. So this is dual encoding. We have both color as well as shape that we've encoded along with our X and Y coordinates of a plotted point. So basically 4 variables here. Then encoding with size. So here we've taken a measure called quantity, and we've drug that over the size marks, and you'll see that these aren't just our standard plotted points. They're circles of different sizes. And what has been encoded here is if the particular quantity is greater or lesser. So if it's greater, we might have a larger circle that's like 14, 15 in size around. And if it's less, it might be a 1 or a 5 in size. So we have different size of circles to give us a sense of how much the quantity was in that particular data point. We can encode labels. So here we've taken plotted points for quantity. Notice that we're now back to all the plotted points are the same size, but we've taken quantity and drug it to the label mark, and you'll see that the quantity for each of those plotted points is now represented in a little label underneath each one of them. So starting at the top, we have one with a 4, so a quantity of 4, one with a quantity of 6, etc. Now we also have what are called details that we can encode. And so what we've done here is we've encoded some details. The visualization that you see on the left, we have 3 different segments that are making up the x-axis. So that's consumer, corporate, and home office. We're looking at profit. And then within each of those segments, we have subcategories. And the way that we got those is we took the subcategory field and drug it over to the detail marks. And we have one highlighted there on the left-hand side. You can see that the overall segment is home office, but then the subcategory is machines that accounted for $152 in profit. Okay. Now, just to make this a little bit more clear, I've dual encoded the same visualization on the right-hand side of the screen. And so you can see the same consumer, corporate, and home office. Those are our three segments on the x-axis. You can see that we're still looking at our profit measurement here. But what I've done is color encode the subcategory. Basically taken subcategory, drug it over to color, and you can see that we have that particular detail there now represented in color as well. And then finally, we'll discuss what is a tooltip. So what a tooltip does is it allows me to define certain data elements that can be made available as a pop-up window when I hover on over a particular data visualization object. In order to get that, I of course would drag a field over to the marks object of tooltip. If you look over on the right-hand side, so we have a simple bar chart there. We've highlighted the bar chart corresponding to the west, and because we've defined particular tooltip values, we've assigned particular fields to the tooltip, they will come up right there. So average discount, profit, quantity, sales, whatever it is that whatever fields we've drugged to the tooltip will be represented when we hover over that particular object. And then in the center of the screen here, I've provided the configuration screen for Edit Tooltip. So whenever you drag something to the tooltip, you'll have this Edit Tooltip screen. You'll see that we have our 4 different fields there: average discount, profit, quantity, and sales. And then in general, at the top, we receive the region label to start off with. And if I wanted to add a 5th measure to this particular tooltip, I could just select the measure and drag it to tooltip, and it would add it to this particular tooltip. So it's a way we can basically hover over an object and see sort of what are some key statistics or metrics about that particular object. And then the last that we haven't really represented here, and it's recently been added, is basically a path. And so in the most current version of Tableau, underneath label and to the right of tooltip, you'll see a mark type called path. We may have had something to do with encouraging its creation. In our class, we have continually done an exercise and assignment for tracking hurricane paths. So at least I like to think we had a little bit of influence on introducing that feature into the software. So then we come to the 4th nested level of visualization, which is the algorithm. And there certainly isn't any requirement to use an algorithm. We don't have to have an algorithm to have great data visualization. We might have manually assigned our data elements to the visual encoding. but we might also want an algorithm to assist us with that process. So in selection of a particular business algorithm, we might have an internal descriptive presentation, something that its purpose is for internal distribution in our company. We might have an external descriptive presentation, something we send out to all our customers, or an internal/external exploratory application. And so we will take a look at one of those that might be a good example of an algorithm. So what we see in front of us is an interactive application that helps to name or basically look at names that people have named their children throughout the, I guess we'd say, the last 120 years. So you can see the different census points, so 1880, 1890s, 1900s, 1910s, 1920s, etc. So in 10-year increments. And the data, the underlying data for this particular algorithm or application are the names that are collected off of birth certificates. So just recently, these data sets have become more available, at least these particular data elements. And what this application allows us to do is enter a particular name. So we see up at the top of the screen the field described as baby name. So we could enter a particular name. We could select the radio button of we think it's a boy's name or a girl's name, or we want to look at it in both contexts. So from there, once we enter the particular name we're interested in and then select the enter key, the algorithm will go take a look at the data set and then represent names that have what's been represented. So I've entered Steve because there's a very popular Steve phenomenon in the United States at a particular point in time. As you can see here, it was very popular to name your baby Steve or Stephen. There's actually a movie that's dedicated to the name of Steve called the Tao of Steve. And for equal measure, my childhood friend, since I was 2 years old, is named, guess what? Stephen. And guess what his father's name is? Yes, you guessed correctly, Steve. So it's a real thing, a cultural phenomenon that's gone on in the U.S. And you can see that represented there, particularly at its peak in the 40s and 50s. You can see per 1 million births, it exceeded 9,000 per million births. And the scale that we're working with here, of course, we have time along the x-axis, along the y-axis. It's a ratio of the number of instances of this particular name per 1 million births. So it gives us sort of a ratio to understand. And to give that maybe a fuller context, so that's 9,000 per million births. And then if you wanted to know how many were in the United States, you might multiply that by however many million people were in the U.S. at that particular time. And so now let's go out and we'll take a look at the Baby Name Wizard. That's the online application for this interactive algorithm, and we'll get a better sense of how it works. Okay, so as we were discussing, we might utilize this particular algorithm for baby names in this way. So we enter Steve, and there it comes. Using another very popular name, here's Susan. And just as a reminder for everyone, so it's represented as a certain number of thousands, so 11,000 at its peak per million births. And then at different points in time, I can see what this name was ranked. So 1960s, third, 1950s, fourth, 40s, 10th, 30s. Hadn't quite caught on yet. It was maybe 117. So you get the example. And so we might have some others. So here's one, and I'll have you guys ponder what some of the cultural reference might be here. So we do see sort of some interesting aspects here where we actually have a number of females that may have been named John, Johnny, Jonna. There's our boys, so some different iterations. Johnny, Johnny, as well as John. Now, I'd given you guys the sort of thinking exercise of what some of the cultural reference might have been here. And some of you folks may have recognized this as a name from the religious text of the Bible. So John was a key character there, and so you can see, particularly historically, a great deal of influence. But as we move into sort of this modern time, maybe slightly less naming influence of that cultural phenomenon. So another character from the same text that's on a slightly different trajectory. So I think we had the name of Brittany that has a particular recent interest. Cassie. I know it's in many of you guys' minds, so I'll go ahead and enter it. We can also check the work to see how we did on naming our sons. I'll ask a couple questions rhetorically for you guys about the encoding. So why do you think, or first maybe we should just start as, what do you think the type of visual encoding is of this data? So think about it a little bit, and then we'll catch up. So some of you guys may have come to the conclusion that we're doing some sort of a trend line or an area chart here. So the area chart is representing the folks that were named underneath. We also use color encoding. And I'm curious if you guys have thought about why the color encoding was blue and pink. And some of you guys may have said, oh man, that's very stereotypical. And I would actually agree with you because for probably the last 2 years, my son Charlie's favorite color has been pink. And if he had his way, he would probably feel like he had been misrepresented by the blue. And as we discussed before, this would be Charlie as female. Martin Wattenberg, who is the creator of this this algorithm, is probably one of the most talented data visualization folks in the community. Why do we think this choice was made? There's probably an obvious stereotype to each of them. So in the United States, there's a long historic stereotype that boys like blue and girls like pink, or boys should like blue and girls should like pink. And for obvious reasons, you know, I would think that the stereotype is outdated. But there's probably a very smart reason why they've done this, and I would gather that Wattenberg and Villegas, his wife that helped build this, contemplated, debated, and discussed whether they should encode with these two colors or not, maybe for weeks on end. But ultimately, they probably came back to the conclusion that for utility, that they should use it, that the stereotype probably does a lot more in the utility of communication and understanding of what data is represented for a general audience than it does harm through the stereotype. And so they have encoded it this way. And I think my objective view is that it works pretty well. It was probably a very good design decision. So along the same subject lines, we have here a discussion with some corresponding data visualization for plotting age distribution. So certainly the algorithm with the baby name wizard that we were just working with is a lot of fun. If you're a parent or have been a parent, prospective parent, you probably have a significant sense of how useful that particular application is. But there might be other types of problems that we want to solve in this same category. So what we see in front of us here, created by Nate Silver from the news media website 538, and it's about plotting age distribution. And what it does is this particular data visualization gives you the distribution of ages of American girls that have the name Brittany. And this is by year of birth. And so what you'll see here is a distribution. So if we look here at the peak, so the median living Brittany is let's say 23 years old, I would guess now. So if that's 1990, might be 27 years old or 30 years old. But what this distribution does is allows us to see the number of Brittany's that were born each year. So we can see up until probably 1970, 1975, Brittany was not such a popular name. So there weren't really any Brittany's until we hit sort of the mid to late 70s, and then we start seeing Britneys. The number of Britneys peak in about 1990, and then begin to slowly drop off and have sort of plateaued in 2010 with maybe sort of a consistent number of Britneys. Maybe there's 1,000 or 2,000 Britneys that are named each year. So this is kind of an interesting take on some of the same data. If you wanted to get a sense of the number of Britneys born each year, or how many Britneys are still alive, that might give you a sense. Using some of the same data, also from Nate Silver, this visualization analysis answers a slightly different question. So let's say that we know someone's name, but we're trying to speculate, we're trying to forecast how old are they. So presented on the left-hand side here, these are female names, so median ages for females with the 25 most common names. So these are the 25 most common names benchmarked at 2014. So we have Emily, Ashley, Sarah, Jessica, Anna, Jennifer, etc., through Helen, Betty, Dorothy. So I'll go ahead and zero in on Sarah. That happens to be the name of my wife. And she would be thrilled to hear that I would speculate that her age would be 26. Now, I might also have to allow that the range of her age might be somewhere between, I'm going to go ahead and say 18 because I feel much more comfortable saying that, and 35. And so that might be the range of people named Sarah, including my wife. So, and proceeding on, maybe with a different example, it gives us a sense on each of these. So this one's highlighting Anna. So persons named Anna, we can see have a much larger distribution. We might forecast that Anna is about 32, but might be a range of maybe 14 to 62 or 63. So this gives you just sort of a fun way of solving a particular real-world problem. If I know someone's name, perhaps I'm meeting them for an interview tomorrow, but I have no idea what age they are. And this might help us just give us a sense of what it might be. And we see the exact same type approach on the right-hand side for males with the 25 most common names. I assure you that mine is not on this list. So we have Joshua, Andrew, Matthew, Christopher, all the way through Richard, George, Donald. The last one, of course, somewhat recently interesting. And we see the median on each of those as well as the range on those names. And taking a look at the last one, sort of notoriety, we might forecast the age of our current public figure to be near 60. Of course, it might be much more senior to that, perhaps 70, or as young as 47 or 48. Now the last one here, also provided by Nate Silver, is titled The Deadest Names. So this is taking the exact same data set that we've been talking about with names and the statistics, and estimating the percentage of Americans with a given name born since 1900 who are now deceased as of 2014. And so if we take a look at the female names, so we have Mabel, Gertrude, Myrtle, Blanche, Beulah, Bessie, Pearl, Ethel, Minnie, and Viola. And on the right-hand side, so it's a simple bar chart. And on the right-hand side, the percentage of those individuals who are now deceased. So Mabel, so if we had a particular, perhaps a grandmother named Mabel, the probability that Mabel is no longer with us is roughly 90%, but who knows? We might be in the lucky 10%. And reading down to the male names down at the bottom, Elmer, Clarence, Harry, on through Claude, Fred, and Sam. My own grandfather, who's, I'll say, in excess of 95, is named Elmer, and loves to tell a story of dating Viola, which you'll see in the next category up, before he met my grandmother, who has passed and is no longer with us. So this just gives you sort of a fun sense of how we might use statistics or probability using the same data set for a meaningful purpose. So in summary, make sure to define your titles and axes for what you want to say. We want to label those axes well. We want to make sure our titles are clear and help to frame the overall visualization. We oftentimes will need to reformat data files to work with our particular visualization tool of preference. So we should get used to this process of reformatting and file interchange. Often we'll clean and format data to a solid executable file. Almost always. However, when we find data files, we will need to clean them and make formatting adjustments. Often when we set upon a project to create data visualization or a data visualization or a data visualization application, we need to leverage knowledge in a data domain. Now, we may have experience in that particular data domain and know the data very well, in which case we can probably leverage our own knowledge. In other contexts, we may not have a full understanding of the definitions and nuances of the different data elements or variables in a data set, and we might want to leverage subject matter experts. Then we might define the user experience. So what kind of user experience do we want for this visualization? Is it simply a sort of read and understand descriptive data visualization? Do we want some type of navigation with it, or overview and drill down? Do we want browsing? So we want to talk about and define what kind of user experience do we want. Do we want an animated user experience? So any of those can be different approaches to the task and data abstraction. We'll determine how we want to structure the data. So particularly this is our data abstraction. How do we want it? Do we want it tableized, cube, network diagram? How do we want to structure that data? And then we'll visually encode it. Do we want it to be lines, plotted points, areas, or different variables of X, Y, Z, color, texture, etc. And then finally, we'll make a decision. Do we want to create and enhance using an algorithm for replication of the experience? And for your benefit, we provided a couple of deeper resources to get a deeper sense of the data. We provided the Seeing Data Working Group, which will give you different types of definitions, as well as we've highlighted a video from Kim Rees called Living, Breathing Data that we encourage you to reference. This concludes the lecture on data manipulation.